I'm going to tell you today about our poster on neural network modeling for the second stage of an L-band amplifier. This work is an extension of our previous results presented at CLIO in 2023, where we looked at a neural net for a single stage L-band amplifier. And of course, for a single stage, the input powers are low. For this work, we're looking at a second stage where the input powers have to be high and where the amplifier in this other regime could act very differently. So we're looking at erbium-doped amplifiers, which are being used in the L-band so that we can expand the capacity of the fiber. Physics-based models for EDFAs are very good in the C-band, but they're less accurate for the L-band. And there's a very good reason for this missing accuracy in the L-band. It's because of the dependence on the GILE parameters. This is required for the physics-based models, and they can be hard to estimate. In particular, in the L-band, we have high measurement error due to the low emission cross-section and also to the presence of excited state absorption. Neural network models, we found in our previous work, are really fast and accurate. When we're designing multi-stage amplifiers, we have to do a lot of simulations, which means that we could really take advantage of a model that ran fast. And so even if neural networks are just as accurate in the C-band as the physics-based, they'll always be faster. So even for the C-band, neural networks could be an interesting choice. So we used experimentally captured training sets to train a neural net to predict the second stage of a two-stage amplifier, and then we used these neural nets to actually run a design, sweep through many design parameters for two distinct performance criteria. So if you come by my poster, I'll tell you all about how we did the collection of our experimental data. We had a fixed first stage amplifier that just beefed up the power. Then we had a programmable wave shaper where we're able to step through different input profiles, which goes into the final second stage of this amplifier where we have different parameters, the length of the fiber, the powers forward and backwards, etc. So our neural network, very standard design, very standard structure. We have a separate neural network for gain and for noise figure, and here are the input parameters, the powers and the length of the fibers. And whether we're predicting gain or we're predicting noise figure, we got very low error, very high prediction accuracy. Then the example that we use is to take these two neural nets that we had, our previous one for the first stage and our current one for the second stage, and run an optimization on them. For this optimization, we actually fixed the parameters, the length, the pump power, etc., for each of these two neural networks. But what we did change is the mid-stage filter. So the mid-stage filter is being optimized, and of course every time we change the mid-stage filter, we have to run our neural net for stage 2 again, which is why the fast running time is very important. So we ran a particle swarm optimization to optimize the performance, and if you stop by my poster, I'll tell you what kind of results we got.